So we're going to talk about the experiences of some OS distributions starting to use LLVM as the primary toolchain. We're going to talk quickly about what distributions I'm talking about, why we decided to go with LLVM for the main toolchain. And then we're going to take a quick look at what is working great for us, and then a bigger look at what is not yet working so great. The fact that this is a bigger look doesn't actually mean that overall it's not working out great, but sometimes the information of what still needs improvement is more important than the information what's already working perfectly. So while we'll see a lot of things in the list of things that are not yet working great, overall it is working great. And nothing of this should be taken as you guys suck. It should instead be taken as it's a great project, and there's still a couple of things that could be improved. So one of the distributions I'm talking about is One-ero, which probably only few people have heard about so far, because we haven't really had a public release yet. It's the Eclipse Foundation's IoT operating system for all scenarios. It can be built on top of Linux, Zephyr, FreeRTOS, and LightOS kernels. So it's targeting pretty much anything from a microcontroller like a Cortex M0 all the way up to higher-end ARM dev boards like a Raspberry Pi. One of the interesting things about One-ero is that it includes a number of blueprints, which is essentially examples showing how it can be used and that can be built into end-user-ready products easily. For example, we have a blueprint for a door lock that could be used to build a smart safe, or that could be used to unlock your house or whatever, or a vending machine. Quite a few more things coming before the first public release, which will happen pretty soon. The upcoming version will use LLVM, clang, LLD, libc++, compiler RT14 as its primary toolchain. GCC 12 and related tools will also be provided for a couple of reasons that I'll go into a bit later. But pretty much everything will be built with the LLVM-based toolchain. This system is Yocto-based, so the system gets built from source all the time, including the toolchain. The other system is OpenMandriva, which is, it has been around for a longer time, so maybe a few more people have heard of it. It's a community developed Linux distribution that is primarily targeting desktop systems, but also anything from higher-end ARM systems like the PinePhone or Raspberry Pi to all the way to the top of the scale, like high-end servers, Ampere Altra, Epic, Xeon. So overall, the talk covers anything from a microcontroller to a high-end server. Target architectures in OpenMandriva are primarily x86-64, ARC64, ZEnver1, which is AMD-specific extensions to x86-64, and RISC-V and PPC are under construction. The current development version uses LLVM, clang, LLD14, also with GCC 12 provided for a couple of special cases. And this uses the RPM package manager, so it's a totally different situation here with binary packages being distributed and the typical end user not seeing much of the tool chain. So currently we are not using libc++ yet, which is for binary compatibility. Because, for example, if we build libc++ as the system SDL, then we build Qt against it, and then someone installs a third-party binary-only application, like a couple of games from Steam or so, and those have been built on a different distribution that uses libstdc++, and it also tries to use Qt. Obviously, that's going to clash, because there will be different symbols, requirements on different libraries that try to provide the same thing. And of course, there are workarounds for that, like you could have a separate directory with libstdc++ linked versions, and then set LD library paths to to pick which you want. But that would be such a pain on the end user that we'd probably end up scaring away all the not so technical users, which is our main user base. So for the moment, we are staying with libc here, while in One-ero, libc is already in use. So why did we decide to do this? First thing is having a more maintainable code base. Probably a lot of people have looked at the LLVM code base. It's always quite readable, quite maintainable, quite easy to find a place where some problem happens, even if you're not spending 24 hours a day working on the code base. Well, I couldn't say exactly the same thing about binutils and GCC, even though they are good compilers as well. Another thing is it's constantly getting better. The master branch can almost always be used to build pretty much everything. While in GCC, you tend to have some periods where lots of bugs are added. And then if you take a snapshot from that time period, you see a lot of internal compiler errors. They ultimately get fixed before the next release. But with LLVM, it's pretty much always possible to take a snapshot of the release that you want in the final product and prepare for that. While with GCC, you're better off sticking with the last stable version and then updating as the next stable version gets ready. Next reason is libraries were needed anyway, so for running Mesa and CReduce and the likes, we needed to build LLVM libraries anyway. So it wasn't having to go through an entirely new project to add everything. LTO, PGO, and sanitizers were an extra plus. Compilation speed was an extra plus at that time, but that is not so much an issue anymore today because Clang got a bit slower as it added more optimizations. And at the same time, GCC got a bit faster. So still not a bad point, but not as important as it used to be. And in the case of OpenMandriva, we decided to switch ages ago. We were the first distribution to make this attempt, and another reason to do it was simply to see if it could be done and what the impact of performance on the entire system would be, which turned out to be pretty much the same as with the GCC build toolchain at that time, and at the moment, that's probably slightly ahead of the GCC build system, but there's also some packages in which GCC still provides better results. So, what is working great? Almost everything. These days, we can pretty much drop in the LLVM tools in Clang, even use them with systems with packages that were clearly meant to be built with GCC, and it will just work. This applies to both Clang and binutils replacements in the LLVM tree. Yeah, the master branch works so well that we can easily build everything with a 15.x snapshot right now, given that we know the next release will happen in the 15.x time frame. One funny thing is that the extensor architecture hasn't actually landed in LLVM's tree yet. It's currently in Fabricator for review, but it's already working better than in GCC, where it has landed in the tree. Because in the LLVM implementation of extensor, we have a compiler switch that can select between different subtypes, whereas in the GCC, we have to patch the code for specific CPU subtypes. So I'm really looking forward to those patches hitting the Git repositories. Next thing that used to be a problem in the past is building Linux kernels. That was quite tricky early on because variable length arrays and structures, but that has all been fixed. There's an active project that makes it better, and even including the LLVM versions of binutils, even linking with LLD works perfectly these days. So there's no reason anymore to build a separate kernel compiler or anything. Next thing is cross-compilers. With LLVM clang, you can build all the target architectures you want into the same binary. No reason to build 200 different toolchains for 200 different targets. But that's only part one. There's another part of cross-compilers that is not yet working that great. We'll talk about that in a bit. Yeah, most third-party projects that used to need to make it built with clang type patches are fixed these days. There's only two things where we still absolutely have to force GCC, which is glibc and elfutils. In the case of elfutils, it's only because of nested functions. So that takes us to the part about what is not yet working so great for those distributions. First thing is glibc. That's really a major pain point. Getting to build with anything but GCC and GNU utils is a lot of work. And it's work nobody seems to be doing. At one point, there was a Google branch trying to do it, but they stopped working on it. That branch is still available, but it's based on a glibc version that is, I think, 7 or 8 major revisions behind. So getting that to the current world will be hard. Might as well be worth starting over. In One-ero, we've solved this for the most part by using Muzzle, which is an alternative libc implementation. In both One-ero and OpenMandriva, we'll be watching out for the LLVM libc. But given binary compatibility with others is an issue, probably glibc will be needed for a long time. And there's no way to just drop glibc for a general purpose system at this point. And unfortunately, there's currently no effort, or at least no effort that anyone in our projects is aware of, to fix glibc or implement the extensions it relies on in clang and LLD. Next thing we've sometimes run into problems with is developers expecting -f permissive to be somewhat more permissive than it actually is. This is probably a problem that primarily distribution packages and the likes, so people who tend to work on code that they didn't write themselves notice a lot. So we find code like casting a null pointer to the bool in C++ 17 code, which is obviously not exactly valid, but it's clear what the user meant. So a lot of people tend to write that sort of things, and quite a few people think that -f permissive should allow it, given it's clear what was intended, and given that in some combinations of flags and other compilers it actually works. Now let's get to cross-compilers part 2. Part 1 was the bits that work great, like building all the cross-compilers into one version, not having to maintain hundreds different tool chains. Yeah, so that works perfectly as long as you're looking at the compiler itself. But then there's some components that you will need to make the compiler really useful, like compiler RT, libc++ ABI, and libc++, and cross-compiling those can get rather tricky. In fact, the CMake files don't do that good a job at cross-compiling them at all, so that most people trying to cross-compile them end up writing separate scripts that just run CMake over and over again with different target options, different toolchain files. And it gets even worse if you need to target specific sub-architectures, like, for example, ARMv7 without Neon and ARMv7 with Neon at the same time, because you don't know what the end user of the toolchain will be looking at. Next point is a lot of people seem to assume that Linux is Debian and Ubuntu. Parts of the LLVM build system tend to assume it, because some stuff like the libc++ headers, config site, and the likes go to directories that only Debian-based distributions would search in. And occasionally we run into build failures if a system library is not exactly what you'd expect to find on a Debian system. So people using other Linux distributions may run into this. And usually that gets fixed quite quickly. If not because of anything, then because we submit patches. But it would be great if the CI system took a bit more of an effort to find this. Next thing is the __ GNU-C issue, and related to that, built-ins. There is the flag -f GNU-C version, which allows simulating a specific version of GCC. And especially when you set that to anything beyond 4.2, some of the missing built-in functions become a problem, because there's a lot of code out there that uses them either unconditionally or with the condition of GCC version greater than 5. Now this brings up the point of why would anyone use -f GNU-C version equals 12 or so? The answer for that is there's bad code out there. I think, yeah. Some projects end up doing this if GNU-C is greater than 7 or greater than 8 or whatever. They do something really smart using AVX 512 instructions on x86 or so, because they know the compiler can handle them. And if not, they just use a workaround that will work on prehistoric compilers. And Clang identifying itself as GCC4 frequently results in missed optimizations in code blocks like that. Which is why in OpenMandriva we've patched the default value to 11.2. And then we end up patching projects that have those missing built-ins as dependencies if you use newer -f GNU-C. Yeah, then next slide pain point is API changes. For someone not following all the commits closely and not too deeply into the toolchain itself, it's sometimes hard to keep track of the API changes. So when trying to make a tool work with newer things, like making C-reduce work with an unreleased version or so, or making Doxygen work, it's not always easy to find the right fix, and it would be nice to have some document somewhere in Git explaining what has been changed and how to adapt code that relies on something that has been used. And lastly, some of the tools have a rather steep learning curve. We like lldb in both projects, but for people who have used GDB for decades, it's just not worth the effort because it doesn't have any really big advantages, so people would rather keep using what they know how to use. And also the tools used by LLVM itself sometimes have a steep learning curve. A lot of people who only do an occasional commit or something can't really figure out how to use Fabricator. And for that, it would be great if people could also accept pull requests that people are generally more familiar with, and maybe just submit them to Fabricator on the submitter's behalf. Yeah, that's what I had. I think we are pretty much exactly in time. There's probably not much time for questions. So if you have any questions, please either be very fast or find me in the floor, and we can have a roundtable if someone is really interested in some topics.
Thank you very much, Bernhard. Do you have any questions?
Oh, he's there. Thanks for the talk. So I have a question. You mentioned a few times that you're building your distro like from top of master. or main from LLVM. So curious, are you also like running like unit tests as part of your like package building process? So you build like package X and you run like some unit tests from there?
Yes. For most packages, we have unit tests, because it somewhat depends on what the upstream projects provide. For some, we have added a few, and most of the time, there's at least some basic tests, and they generally work pretty well, even with master.
I was mostly curious, like, if you see tests, and then, like, if you do this incrementally, like, you build a new main build, like, from top of tree, and then you run the, like, unit tests, do you sometimes, like, or, like, what is your experience of how often you get failures from, like a green main branch, and then you still have packages that fail? So essentially, like, you get bugs that are missed by the test suite. If you have, like, no stats, but I was just kind of curious what your, like, feeling for this is.
That happens all the time, but most of the time it turns out to be actually a bug in the code that's being compiled that just happened to work with the previous version, because it's triggering undefined behavior. Sometimes, for an actual compiler bug, maybe when we switched over to the 14 branch in November or so, we are now at the 14.03 release, we found 1 or 2 packages that didn't actually compile because of actual bugs. So that's really looking good.
Thanks.
We would have time for one short question.
Yeah, thank you. If there's anything else, just find me. I'll be around all the time.
Thank you again.